Good afternoon. I am Ingrid Moerman from IMEC, and I will present the final results of the CODYSUN project. The full title of the project is Collaborative and Dynamic Approaches to Increasing Spectrum Utilization. This project was performed by IMEC as a coordinator with Antwerp Space and Connect as subcontractors. Let me first explain why we have done this study. This study was driven by the successful participation of IMEC in the DARPA Spectrum Collaboration Challenge, where we have designed and implemented a full end-to-end system and where we have proven that dynamic and collaborative approaches can lead to much more efficient spectrum utilization for terrestrial scenarios. The main focus of the DARPA challenge was to design a solution to move away from exclusive use of spectrum in isolated spectrum bands, which leads to overdimensioning and waste of spectrum. Spectrum is a scarce resource, just like water. We can compare exclusive spectrum with taking water with a spoon while the water tap is fully open, leading to a huge waste of water. The DARPA challenge has proved that by breaking the barriers between spectrum silos and sharing spectrum, spectrum utilization can be largely increased. Combining a large pool of shared spectrum with high spatial reuse gives us more freedom for resource allocation, which becomes more clear when looking at spectrum utilization from a single system point of view or a single receiver point of view. Why is a receiver view so important? Because interference is only happening at the receiver. The receiver has the best view on which spectrum can be used and which spectrum should be avoided. Today, satellite systems are using a fixed narrow spectrum band and most of the resources are allocated. In case of an interference event, it is hard to reshuffle the resources. In CODYSUN, we assume a large shared spectrum band with sparse resource allocation, which has more freedom for resource allocation. In case of an interference event at the receiver, it is easy to move the resource to a non-interfered slot. And thanks to the beamforming properties of satellite communication, a high spatial reuse of spectrum is possible. Which brings us to the CODYSUN objectives. The main goal was to investigate the benefits of dynamic spectrum access techniques in Satcom, which can be broken down in 3 sub-goals. First, identify relevant Satcom scenarios and use cases. Next, analyze the performance of dynamic spectrum sharing for these use cases. And finally, formulate a strategy to enable dynamic spectrum sharing, taking into account the regulatory framework. 2 use cases have been selected for further analysis. Use case 1 consists of multiple satellite systems, GSO as well as NGSO, that share the downlink Ka band with terrestrial millimeter wave systems. The satellites are serving multiple mobile Earth stations in motion. When sharing the same band, there can be interference from satellites to Earth stations and from millimeter wave links to Earth stations. The second use case is the same scenario, but now we look at the uplink. In this case, we can have interference from Earth stations to satellites and from Earth stations to terrestrial millimeter wave links. We have analyzed the 2 use cases by a simulation study. We defined a scenario with any possible interference event, kind of worst-case scenario. We considered one geosatellite and two NGSO satellites in different orbits, each communicating with one Earth station in motion, called ESIM. Each ESIM starts at a different location and moves to the right at typical train speeds. Different interference events can happen. During the first event, all satellite links are aligned. Next, the eSIMs approach a first terrestrial millimeter wave link, which has a 30-degree inclination with respect to Earth. eSIM 3 stops at the millimeter wave length, while the other two eSIMs pass by and further also past the second terrestrial millimeter wave length, which is parallel to Earth. The scenario becomes more clear with this video. In the first part, you can see the three satellite links, how they move and how they align. In the second part, right? So in the second part, you can see the moving eSIMs and the terrestrial links with one NGSO eSIM stopping at some point in time at the location of the inclined millimeter wave link, while the others keep moving. Without going into details, this slide shows the major assumptions with respect to PHY models and MAC schemes. We implemented ITU antenna models and built models for co-channel and adjacent channel interference, propagation delays, RRSI measurements, and spectrum sensing. We further considered multi-frequency TDMA and frequency DDMA MAC schemes. Application loads were dynamic, with application demands changing over time. Unlike common database approaches based on centralized databases, we adopted a distributed approach by building a local interference map. This can be seen as a distributed database that only collects information relevant for that receiver. The CODYSUN approach is event-driven, meaning that the system only reacts when interference is detected at the receiver. When an interference event is detected, a new link is established. Three approaches have been studied. DSS1, which is a decentralized collaboration protocol that sends advertisements with information on transmissions. The protocol also allows a receiver to send alert messages in case interference is detected. DSS2 only uses spectrum sensing information to build the local interference map. And DSS3 is the combination of DSS1 and DSS2. Due to the event-driven approach and a fast reaction time, the proposed distributed approaches are expected to be more scalable. We have evaluated the performance for the two use cases and for the different DSS techniques through an extensive simulation study. First, we analyzed a baseline scenario without applying DSS techniques, meaning a fixed channel allocation. The graphs show the signal to interference plus noise ratio versus time. For the downlink use case, we can see the impact of the different interference events highlighted in different colors. When different satellites align, when a satellite and the inclined millimeter wavelength align, and when the eSIM 3 stops at the inclined millimeter wavelength. Interference events clearly have a huge impact on the link quality and lead to periods with large packet loss and non-acceptable downtimes. By applying dynamic spectrum sharing, we can see that the impact of interference is almost fully eliminated. Only the GSO eSIM still suffers from out-of-band interference by the inclined millimeter wavelength. And thanks to a fast reaction time and reallocation of spectrum, downtime can now be kept very small. Here we can see the results of a first set of simulations where we limited the number of shared channels to 3. In the downlink use case, all DSS techniques are capable to protect the satellite links. Also, terrestrial links do not suffer, even not in the baseline scenario. Protection in the uplink use case seems to be more complicated. Only the geolink and the parallel milliwave link is well protected. The NGSO satellites suffer from out-of-band emissions from the GSO eSIM emitting at high power. The inclined terrestrial link suffers from the nearby eSIMs that use much higher emission powers compared to the terrestrial links. As we only have 3 channels in our simulation scenario, it is impossible to avoid out-of-band emission. Therefore, we also analyzed DSS scenarios with 5 channels. On the left side, you can see the results for the 3 channels. On the right side, the results for 5 channels are shown. There is a clear improvement, as now the out-of-band emission can be mitigated by avoiding the use of neighboring channels. Unfortunately, it is still hard to protect the inclined millimeter wave link, which still suffers from interference by the strong GSO link. And no interference events is triggered since the GSO link is stable and not aware about the terrestrial links, so it doesn't take any action for reallocation of spectrum. That's why the DSS-1 technique has been extended with 2 extra protection mechanisms. The first extension requires the terrestrial network to send an alert message for triggering the GSO to move to another channel. A second extension also mitigates out-of-band emission besides sending an alert message. With these 2 extensions, the terrestrial millimeter wave links can be perfectly protected. Which brings us to the conclusions. CODYSUN dynamic spectrum sharing solutions largely increase the uptime or reduce the downtime compared to fixed spectrum allocation. Recovery from interference is fast, at least when the interference is generated by known satellite and terrestrial systems. If the receiver has spectrum monitoring capability, interference of unknown system can also be mitigated. CODYSUN approaches have several benefits. They are PHY agnostic, they only require lightweight interoperability, and they are scalable, only taking actions triggered by events, and they also exploit spatial reuse. The approaches can be easily adopted in current satellite systems by software modifications at the ground stations only. There is one drawback. A short period of downtime is still possible, but there are mechanisms to reduce this time. Finally, I only want to share some recommendations. It is time to move to experimental verifications. Assumptions used in simulations need to be experimentally validated. At the regulatory level, a spectrum band that can be used for dynamic spectrum sharing experiments is highly desired. It is important to quantify the gains of centralized versus distributed approaches based on experiments and large-scale simulations. And we should also not ignore that the receiver can measure the ground truth, which is more accurate than any transmit model. I want to end with a quote from Paul Tillman, the organizer of the DARPA Spectrum Collaboration Challenge. So, it's time to prove DSA solutions. Thank you for your attention.